Okay, so it's 11 a.m. We can start now. Pleased to introduce Anton Bernshteyn, who will talk about distributive combinatorics and descriptive combinatorics. I swear I know this one. Descriptive combinatorics and distributed algorithms.
Thanks a lot, Anush. Thank you everybody for coming. Thank you for having me give this ASL invited address, and it's exciting to see so many of you, even though it's virtual. And if you have any questions at any point, feel free to either ask them in chat. I'll try to keep an eye on that, or unmute yourself and just speak up, and that would be totally fine. Yes, so I'm going to talk about descriptive combinatorics and distributed algorithms. And these are two areas that might seem kind of unrelated to each other. Descriptive combinatorics is a part of descriptive set theory, and distributed algorithms are something in computer science. But actually, the main point of this talk is that they're intimately related to each other. So, but before I can get into the relationship, I need to explain what each of these two are separately. And I'll start with descriptive combinatorics. In descriptive combinatorics, we'll look at combinatorial problems on infinite graphs with certain extra properties. And for this talk, the main example of a combinatorial problem is a question of proper color in a graph. And I'm going to focus on the case where we're using finitely many colors. So k is some kind of natural number, and just to remind you, a proper k coloring of a graph G. Well, one way to think about it is a partition of the vertex set into k subsets, say V1 through Vk, such that no edge of the graph joins two vertices from the same part. In other words, each set Vi is in what is called an independent set in the graph. So there are no edges contained entirely inside of the set Vi. And the reason why it's called a coloring is because you can think of it alternatively as we have a set of a palette of k colors numbered 1 through k, and we assign color 1 to the vertices in the set V1, color 2 to vertices in V2, etc. And now the condition that these sets are independent is equivalent to saying that adjacent vertices have to get different colors. So what we're trying to do, we're trying to minimize k, minimize the number of colors we need, and the smallest such k is called the chromatic number of the graph and denoted by chi of g. And throughout the talk, I'm going to assume that such k exists. So of course, if the graph is finite, then there is a finite number of colors that you need that is enough, because you can color all the vertices differently. But in infinite graphs, sometimes finitely many colors are also sufficient. And all the examples that I will deal with will be of this sort. So there will be an actual finite, chromatic number will be finite. So this is a extremely well-studied notion in graph theory, but mostly people look at it when the graph G is finite. And part of the reason is that in some sense, maybe you can expect nothing new to happen to infinite graphs, at least if the number of colors is finite. So this is what's called the De Bruijn-Erdős theorem. Given any natural number k and an infinite graph G, this graph G is k colorable if and only if every finite subgraph of G is k colorable. The k colorable means that it has a proper k coloring. And the proof, nowadays, by now this is really sort of an exercise. It's a simple compactness argument that gives you this. But still, it's a noteworthy fact, and in particular, it somehow indicates that maybe, if you want to study colorings of infinite graphs, you just need to understand what happens with the finite subgraphs somehow. So infinite questions reduce to finite ones. Well, actually, and that's the whole point of descriptive combinatorics. Even though this statement is true, there are still questions that you can ask about colorings of infinite graphs, even with finitely many colors, that do not immediately reduce to finite questions in this way. There are some new phenomena that occur, and some of those phenomena are studied in descriptive combinatorics. So the best way to introduce these is through an example, and so I'm going to describe a particular example in some detail. It's a standard example, and I apologize to the experts in the audience for maybe boring them with the next few slides, but there is a reason why I want to get into some amount of detail about this, and hopefully this reason will become apparent in due course. So let's consider a particular infinite graph G. Here, I'm going to define a specific infinite graph, and I'm going to understand what happens with its coloring. So first, let me tell you what the vertex set of this graph is. The vertices of my graph are going to be infinite sequences, infinite binary sequences, infinite sequences of zeros and ones indexed by the integers, both positive and negative and zero. So sequences by infinite sequences of this form, with the extra condition that the sequence should be aperiodic. In other words, it should not look like a finite, some kind of thing just repeated infinitely. So, for example, something like this could be a part of a sequence that is a vertex of my graph, and this is supposed to be just 0, 1, 0, 0, 1, 0, 0, 1, 0, etc., repeated indefinitely in both directions. So this is a periodic sequence, and so it's not one of the vertices in the graph G. And in this, when I write it like this, if I just write the sequence in this way, it wouldn't be clear where the starting position where x0 is located, right? So I'm underlining the position of x0. So in this case, x0 is 0, x1 is 0, x2 is 0, x3 is 1, x negative 1 is 1, etc. Okay, so all of these aperiodic sequences form a vertex set of my graph. Of course, most sequences are aperiodic. There are only countably many periodic sequences. But you will see that in a moment why I want to remove the periodic ones. So this is the vertex set. Now, how am I going to define the edges? Well, here's what I'm going to do. Given a vertex in my graph, which again is a binary sequence like this, I define S of x to be the result of shifting all the entries of the sequence to the left by one position. So, S applied to a sequence that looks like this becomes, something like that. Every digit is shifted by one to the left. Or you can think about it as like shifting the position of the center position of x0 to the right by one. It's the same thing. And the edges of my graph are defined by just putting an edge between every sequence vertex x and S of x. If I start with any vertex x, what does the graph actually look like? Well, x is adjacent to S of x, which in turn is adjacent to S squared of x, so the shift of x by two positions, I guess, which is adjacent to S cubed of x, etc. And also we can go the other direction. X is adjacent to S inverse of x, which is just x shifted to the right by one, which is adjacent to S to the power negative 2 of x, etc. And this is where I'm using that x is aperiodic. The point is that because it's aperiodic, if I shift it by some amount, I get a different sequence. So all of these vertices shown in this picture are actually different from each other. And so the connected component containing x looks like a path that is infinite in both directions. So yeah, that's what I just said. Each connected component of this graph is an infinite path. Again, this is because I'm only focusing on aperiodic sequence. Yeah, I should say that if this looks like somewhat of an ad hoc definition, this shift graph, what it's called, is actually it's an important example both in descriptive combinatorics and in particular it comes from dynamical systems. Actually, it's an important example of in the study of dynamical systems. So it's not as arbitrary as it may seem. Okay, so this is what every connected component of my graph looks like. So in particular, I should know that there are uncountably many components, of course, because there are uncountably many vertices, continued many, right? But every component is a path, it's countable. So it's very, very much a disconnected graph. Now let's understand what happens with colorings. What is the chromatic number of this graph? Well, I need to color the vertices in such a way that adjacent vertices get different colors. Of course, I can do this with two colors. In every path, I can just color, every component is a path, and each of them I can color the vertices by using alternating colors, say red and blue in this picture, red, blue, etc. The chromatic number is 2. And just to say it again, what this means is that I can partition the vertex set of my graph into two independent sets, say the red set and the blue set. So now the type of question that a person in descriptive combinatorics would ask is something of the following sort. Well, okay, we have such a partition into red and blue vertices, so fix any such partition. And now, remember, my vertices are sequences of zeros and ones. I can pick one randomly by just flipping it, tossing a fair coin for every position. So I have infinitely many independent random coins, which with probability 1/2 are heads and probability 1/2 tails, each of them, right? And using these coins, I determine the sequence of zeros and ones randomly. Let's call this X. It's a randomly generated vertex of my graph. What is the probability that this vertex is colored red, right? It's colored something, either red or blue. What's the probability that it's red? If you've never thought about these questions, maybe the first guess, I think, most natural one, is to conjecture that maybe the red and the blue vertices are, I mean, they're alternating in each path, right? So half the vertices should be red, half the vertices should be blue, maybe. This is a natural guess, in some sense, the only reasonable one. But turns out that this guess is incorrect, and it's incorrect for a complicated reason. It's not that the answer is numerically different, that the probabilities are some kind of different values. The probabilities are not defined at all, because these sets R and B necessarily have to be non-measurable. So you cannot actually talk about the measure of the red points, or in other words, the probability that the random points fall into the red set, or the measure of the blue points. This is not a well-defined. These two numbers are not well-defined. Are there any questions so far? So, and as I said, I would like to go into a little bit of detail. I'm going to give you a sketch of the proof why these sets have to necessarily be non-measurable. It's not very complicated, and I just, I want us to see some picture that will appear again later in the talk. So suppose that they are measurable. Well, if they are measurable, then indeed the measures of these sets have to be equal to 1/2. The reason is that, well, what's the probability that a random vertex falls into, is colored red? Well, I claim that it's the same as the probability that the shift of a random vertex is colored red. And this is because what is this S of X? X is we just flipped an infinitely many random coins. And S of X, we flip infinitely many random coins, then we shift them. Well, I mean, it's the same as still flipping infinitely many random coins. We just relabel them somehow. So the probability that X is in R is the same as the probability that S of X is in R. But X and S of X are adjacent, so S of X is in R even only if X is in B, so these two probabilities are equal. And if X is in B, it's the same as to say that it's not in R, so this is equal to 1 minus the probability of it being in R, and now from this equality, we see that the probability of X being in R has to be 1/2, and the probability of X being in B is 1/2 for the same reason. So if the sets are measurable, their measure has to be 1/2 indeed. In that sense, our initial guess was correct. I'm going to introduce this notation. Let's say C of X is the color of vertex X. So C of X is red if X is in R and blue if X is in B. So the tool from measure theory that we need to analyze the situation is the Lebesgue density theorem. And well, it's a general statement about arbitrary probability spaces. But in this case, you can formulate it as follows. So what does this say? Suppose that I give you a vertex of my graph. This is an even sequence of zeros and ones. In general, to determine whether its color is red or blue, we have to look at each of these entries of the sequence, infinitely many digits that are involved there. But maybe what you're trying to do, you're trying to just make a pretty good guess of whether the color is red or blue by looking at only finitely many of the entries of the sequence. And that's what the Lebesgue density theorem allows us to do. So assuming that these two sets are measurable, it provides us, it says that for each epsilon, given epsilon bigger than 0, you can find a natural number t and some kind of guessing function that is given a finite sequence of zeros and ones of length 2t plus 1 outputs a color either red or blue, such that if you take a random sequence x and then you look at the entries at the positions -t, -t plus 1, etc. up to t, so these are 2t plus 1 bits from the sequence that you look at. If you apply the guessing function to them, and the guess is some color, either red or blue, the probability that the guess is wrong, i.e. different from the actual color of x, is less than epsilon. So again, it just says that you can make a pretty good guess, very unlikely to be wrong about the color of x, just by looking at this sufficiently large finite chunk of the infinite sequence. This is just a property that measurable sets. Does it make sense? All right. So armed with this, we can finish the argument. So take a really small epsilon. We'll see how small we need it, and let t and guess be given by the Lebesgue density theorem with this epsilon. So guess is this guessing function. What are the odds that we're guessing that the color is red? Well, the probability that the color actually is red is 1/2, and we are only wrong in our guess with probability less than epsilon. So the probability that we're guessing red has to be at least 1/2 minus epsilon. Of all of those red points, at least this many, this often we have to guess the color to be red. Now here's the crux of the proof. Let's take a really large odd integer n. Really large is bigger than 2t is what we need. Since it's, why do I want it to be odd? Because since it's odd, x and x shifted n times always have different colors because the colors alternate. If x is red, then its shift is blue, next shift is red, etc. So if you shift it odd many times, the resulting vertex has to have a different colors. So these two always have different colors. That's on the one hand. On the other hand, we can try to guess the color of x and the color of s and of x. How do you guess the color of x? You need to look at this interval from from x negative t to xt in the sequence x, right? Look at these entries and use them to guess the color for x, right? And to guess the color for Sn of x, what is really happening, I mean, you shift the sequence and then you look at this interval, which is the same as to say that you're looking at the entries around the nth position. So from xn minus t to xn plus t. And you apply the guessing function to this interval. And because n is so large, these two intervals are disjoint from each other. So when we generate x randomly, this is, this interval contains some sequence of random bits, and this some sequence of random bits. These bits are independent from each other. So the probability that this is red, say, and this also guesses red, is equal to just the product of the individual probabilities, which becomes at least 1/2 minus epsilon squared. That's 1/2 minus epsilon for each of them, and then I'm multiplying these two numbers. And epsilon is very small, so this is roughly 1/4. So what does this mean? This means that both colors actually are red, with probability at least that we guessed both of them to be red, minus the probability that we made at least one of them guessed incorrectly, which since incorrect guesses have this probability epsilon, we need to subtract 2 epsilon here, right? So it's at least this quantity. Epsilon is really small, so this is still roughly 1/4. Definitely for small enough epsilon, this is positive. And we're done. Now this is a contradiction. There's a positive probability that both x and s and x are colored red, even though they have to be colored differently. All right. Does it make sense? So I went into this. The thing I want you to take away from this argument is this picture, because we're going to see a very similar picture in a few slides. We're looking at this interval. What is really important is that there are these disjoint small intervals that somehow, you can determine outcome colors of two vertices by looking at these intervals joined, and because of this, we arrive at a contradiction. To finish up this example, I've argued that you cannot, if you want the individual sets in the partition to be measurable, then 2 sets are not enough for this graph. How many are enough? That's a natural question. Turns out that 3 is the right answer. I think just one more already suffices. One way to say this is to say that the measurable chromatic number of this graph is 3. I will not explain how this works. This is an exercise to the audience. All right. So now, more generally, descriptive combinatorics deals with these sorts of problems, with combinatorial questions such as combinatorial problems such as proper graph coloring under extra regularity constraints such as measurability. And if you're interested, there's this dynamic survey by Kekris and Marx that covers a lot of state-of-the-art results in the area. So again, the main combinatorial problem I will look at in this talk is proper graph coloring as a main example. But there are different types of regularity constraints I want to mention. So one that we already have seen is if the vertex of the graph is a probability, if the graph is a probability space, then we can talk about measurable chromatic number of G, chi sub m of G, and this is like the chromatic number, but these sets in the partition, the color classes, have to be measurable sets. instead of measurable, one can be even more ambitious and ask for Borel chromatic numbers. So if the vertex set is a standard Borel space, you can consider Borel colorings, which is partitions into Borel independent sets now, and the smallest number of sets in such a partition is called the Borel chromatic number of G, chi sub B of G. So one way to think about the relationship between these two is that the measurable one is like a Borel mod null, right? Because measurable sets are like Borel sets modulo null sets. So in this sense, the measurable chromatic number is a relaxation of the Borel chromatic number. There is a different way of relaxing Borel chromatic number by using topology instead of a measure. If the vertex set is a Polish space, then we can define bare measurable chromatic numbers, which are chi sub B of G, which is like Borel mod meager. So now every set has to be Borel modulo meager set. Every color class has to be Borel modulo meager set. And on the other hand, instead of relaxing this Borelness condition, we can strengthen it even further. Sometimes it makes sense to talk about continuous colorings and continuous chromatic numbers. So what does this mean, that continuous chromatic number, right? Since we're using finitely many colors, well, you know, you can think of the set of colors as a finite discrete space, and then really the continuous coloring just means that every color class, every one of these independent sets in the partition has to be a Clopen subset of the vertex set of the graph. That's what this is. So not just Borel, but actually Clopen. And for this to make sense, we need to have, well, the vertex set has to be, say, polar space, but also there have to be enough Clopen sets there so that this is not a trivial question. And it's natural to look at zero-dimensional polar spaces specifically, where, just to remind you, zero-dimensional means that there is a basis for the topology consisting of Clopen sets. So there are a lot of Clopen sets there, and so it makes sense to ask for partition into Clopen independent sets. All right. So what are the sorts of things one can prove? Just to say a bit more about this area, what are the type of results one proves in descriptive combinatorics about these numbers? Well, one of the typical things to do is to look at things we already know about finite graphs and try to understand whether or not similar results hold with these additional regularity constraints. So one of the oldest results of this form is the theorem of Kekker-Seletsky and Todorchiev that says that Borel graphs of finite maximum degree, delta, have Borel chromatic numbers at most delta plus 1. So here, by Borel graph, I mean the graph whose vertex set is a standard Borel space, and whose edge set, where we think of edges as pairs of vertices, so it's a subset of the Cartesian square, Vg cross Vg, and I want it to be a Borel subset, and then the graph is Borel. And the maximum degree of a graph is the maximum number of neighbors that the vertex in the graph can have. So without the Borel requirement of, say, G is a finite graph, it's very easy to see that the chromatic number is most delta plus 1. Just color vertices one by one, and you never run out of colors because every vertex only has delta neighbors. So maybe those are already colored somehow, but there are delta plus 1 colors available for this vertex, so at least one color is left. But it turns out that you can modify this greedy algorithm to actually get Borel colors. Is this bound sharp? Well, yes, for sort of trivial reason, that the graph is maximum degree delta can contain what's called a delta plus 1 clique. It's a set of delta plus 1 vertices, all of which are adjacent to each other. And of course, if you have these vertices that are all adjacent to each other, they all have to have different colors. So you need to use delta plus 1 colors to color such a graph. We will forget about the Borel part, just abstractly. In finite combinatorics, it is well known, it's a classical result that at least when delta is at least 3, these delta plus 1 cliques are the only obstructions. So this is a theorem of Brooks. If G is a graph of finite maximum degree delta that's at least 3, then its chromatic number is actually at most delta rather than delta plus 1, unless G contains a delta plus 1 clique, unless there are delta plus 1 pairwise adjacent vertices in the graph. Yeah, so this is Brooks' theorem again. And so the sort of thing that descriptive combinatorics task is whether we can get, say, a Borel version of this theorem. Can I prove the same thing for Borel chromatic numbers? Turns out that the answer is no. This is a remarkable theorem of Andrew Marx. He constructed examples for each natural number delta of a Borel graph G of maximum degree delta, whose Borel chromatic number is delta plus 1, as large as it can be, So even this +1 cannot be removed. And the graph not only doesn't contain the delta +1 clique, in fact, it doesn't contain any cycles. Every connected component of the graph is a tree. All right. So Borel, the answer is no. What about measurable? If we're less greedy, we want measurable calories. This is their measurable version of Brooks' theorem. Turns out that the answer is yes, which maybe is a bit surprising because it shows that somehow the pathologies of these examples that Mark constructed really have to live on the measure zero set. So this is the theorem of Conley, Marx, and Tucker-Grove, which is literally the same as Brooks' theorem, but with measurable inserted in the appropriate place. G is a Borel graph of finite max degree delta at least 3 on the standard probability space. Then it's measurable chromatic numbers in most delta unless G has a delta +1. All right, so this is sort of a sample of results, and this is a general thing we do. We look at things we might know about finite graphs and try to extend them to infinite graphs in this way with additional regularity constraints like better Borel and measurable. Oh, by the way, here instead of measurable, I could have said bare measurable, the same theorem. All right, so this is a brief introduction to descriptive combinatorics. Next, just distributed algorithms, the second player in this talk. So now the situation is, the setup is quite different. Everything is going to be finite. This is a distributed computing is a part of computer science where we deal with finite structures. So this is what a graph looks like in the imagination of a person who works in distributed algorithms. Every vertex in the graph represents a computer or a processor, say, and edges are some kind of communication links between them. Now we're still trying to solve a combinatorial problem in this structure, say a colorless graph, assign colors to vertices so that adjacent vertices have different colors. But now, and that's why the word distributed is used, every vertex has to decide for itself what color it's going to have. The difficulty comes from the fact that the vertex doesn't actually know what the graph looks like. The only information it has access to is these communication links to its neighbors. So what it can do, it can send messages to the neighbors, and it can receive messages from them. And with this information alone, after some number of these rounds of exchanges of information between the vertices, it has to decide what color it's going to have. I'm going with the color red or something. And every vertex has to make this decision somehow in such a way that these decisions are consistent, that adjacent vertices still have different colors. So that's what distributed algorithms are supposed to do. And what we care about is how much of a exchange, how many rounds of sending messages are needed to find such a color. So to summarize again, this model of distributed computation is called the local model. It's stylized like this in all capitals. So what is the setup? We're working on a finite graph with n vertices, where we think of every vertex as representing a processor, edges representing communication links between them. The computation proceeds in rounds. On each round, the vertices, having the information available to them, perform arbitrary local computations. It doesn't matter how complicated. We think that vertices have infinite computing power. They can do any computation immediately. And then they simultaneously broadcast messages to their neighbors. So every vertex composes messages to its neighbors, and then they all, in the whole graph, simultaneously send and receive messages from their neighbors. And now using this extra information, they again do a computation, send new messages, etc. At the end, after some number of such rounds, every vertex has to output its own part of the solution to the problem. So in other words, its own color. And the complexity of such an algorithm is measured by the number of rounds required. So that's the only thing we care about, how many rounds you need. Well, as I said, the vertices don't know what the graph is, and all of them are performing the same algorithm. So this means that we need some kind of symmetry breaking protocol, some ways of distinguishing vertices from each other. Otherwise, if the graph is a complete graph, right, every vertex will be the same. How are they going to decide which one is going to have which color? There are two standard approaches to symmetry breaking in this model. In the deterministic version of the model, the vertices are distinguished by identifiers. So every vertex is given and is known initially, knows initially, an identifier, which is just a sequence of bits of logarithmic length, length proportional to log n, and it's guaranteed that these identifiers are all different. The algorithm has to work correctly regardless of what the identifiers actually are, as long as it's guaranteed that they're all distinct. Another variation of this model is the randomized version, where instead of the identifiers, each vertex is given a random number generator. So it can generate a sequence of random bits, arbitrarily long sequence of random bits. And these sequences are independent from each other for different vertices. So now, of course, this is a randomized setup, so we cannot say that the algorithm must always succeed because, maybe all the vertices generated exactly the same sequence, right? This could happen, and then they're still not distinguished from each other. But we only require the algorithm to succeed with probability that is close to 1, where the standard threshold is at least 1 minus 1 over n, where n is the total number of vertices. So in particular, the randomized model is stronger than the deterministic one, because any deterministic algorithm can be simulated in the randomized version, where you just, every vertex generates a sequence of bits of length, say, 10 times log n, right? And with probability very close to 1, you can see all these sequences are going to be distinct from each other, so they can be used as identifiers. And so you can run the deterministic algorithm using those sequences. Okay, does this make sense? Are there any questions about the model? So to give you an, before the example, why do we call it the local model? Well, the reason is that one way to think about it, this is capturing, the locality of the problems. It tells you how far each vertex needs to see in the graph in order to decide what its color is going to be. So the reason is that if the algorithm runs for t rounds, well, in one round, the vertex can communicate with its neighbors, right? In 2 rounds, it can send information to its neighbors, and then they will send information to their neighbors. So sort of information travels 2 steps in the graph. And in t rounds, information can only travel up to distance t. So really, a vertex gets only access to what its radius t neighborhood in the graph looks like. Well, then conversely, you can rewrite the algorithm by saying that it sort of just collects all the information contained in this radius t neighborhood, and then based on this information, it decides what its color is going to be. So really, you can think of local algorithms as these sort of functions. A t-round local algorithm is a function that, for each vertex, it takes as input its radius t. For each vertex x, it takes as input the radius t ball around x. Well, the isomorphism type of the radius t ball around x, where these extra, the symmetry breaking information like IDs or random bits are included in the structure. So each vertex, say in the deterministic setting, each vertex here will have its ID written on it, right? And given this information, it has to output the color for it. And if you apply this function to adjacent vertices, then the colors have to be different, I guess. Okay. So as an illustration, let me show to you that if I take a path of length n, or I guess the path with n vertices, there is no way to color it with 2 colors using such an algorithm in significantly fewer than n rounds, a little of n rounds. Of course, you can do it in n rounds, because in n rounds, every vertex can communicate with every other vertex. But in much fewer than that many rounds, it's impossible. Here's why. This is going to be proof sketch. Quite literally, it's just going to be a picture. So imagine this is my path of length n, and suppose I have such an algorithm, say a deterministic one. The argument for randomized algorithms is essentially the same. So what does this algorithm do? Say, look at any individual vertex in my graph on this path. It will look at this interval around it of length little of n, and it will look at what the identifiers of the vertices in this interval are. And based on this information, it's supposed to come up with a color for it, right? Well, because this is little o of n, I can fit several, lots of these intervals disjoint into the path. And in fact, I can even have enough wiggle room to even have, say, one such interval whose center is an even distance from this vertex we started with, and another one whose center is an odd distance from the vertex we started with, right? So this vertex determines its color by looking at this interval, and this vertex determines its color by looking at this interval. Why did I make this distance even and this one odd? Because since this distance is even, we're producing a proper 2 coloring, so these 2 vertices would have to have the same color. Whereas these two vertices would have to have different colors, always. But now you see what the problem is. Why don't I just switch the assignment of identifiers to the vertices of this graph? I take this subinterval and copy these identifiers here, whereas these identifiers go here. All the identifiers are still distinct from each other, but now this this middle vertex is looking at whatever identifiers the rightmost vertex was looking at before. So it's going to output a color, the same color as the rightmost vertex was outputting previously, which is different from the color of this first vertex, even though the distance between these two vertices is even. And that's a contradiction. Does it sound reasonable? So notice that this picture should ring some bells. Now we're returning back to what happens in descriptive combinatorics. Remember, we had a very similar picture when we were proving that this shift graph does not have a measurable two coloring. There was this path, and there were these two subintervals that were disjoint from each other that somehow determined the colors of the corresponding vertices, and that was the source of the problem. So a very similar thing is happening here. The similarity doesn't actually stop there. Remember, I said that the shift graph has a Borel, well, I said measurable, but actually a Borel coloring with 3 colors. Well, the same is true in this setting for paths. A path of length n can be colored with 3 colors in a very small number of rounds. Okay, there's a question in the chat. Doesn't this say we need at least roughly n over 3 rounds? Yes, indeed. It's just easier to think about little of n, but you can be more precise with the constant. In fact, it's roughly n over 2. You can show by a little bit of tweaking of the proof. Yeah, but if you want to color a path with 3 colors, then you can do this very quickly. So this log star n is the iterated logarithm of n, which is the number of times the log function has to be applied to n so that the result becomes less than 1. In other words, it's the inverse of the tower function. It's a very, very slow growing function. Although it does go to infinity with n, but somebody said has never been observed to do so. And by the way, this is asymptotically optimal also. But the main point is that this is extremely efficient once you want 3 colors, and this algorithm is deterministic. But with 2 colors, nothing reasonable can be done. All right. Okay, so this is again parallel to what we discussed in descriptive combinatorics. Again, the parallels continue actually. Remember, I mentioned this theorem of Kekker-Seletsky and Todorchevich that Borel graphs of maximum degree delta have Borel colorings with delta plus 1 colors. Well, a similar thing is true for distributed algorithms. For fixed delta, so fixed delta for this slide, then there exists a big O of log star n round deterministic distributed algorithm that colors graphs of maximum degree delta using delta plus 1 colors. Now you can ask what happens with if you want delta coloring rather than delta plus 1, can we get a Brooks theorem version? And the answer is no for deterministic algorithms, at least if we want it to be more efficient than log n, the number of rounds to be little of log n. This is going to be the threshold we will be looking at. So this is very far from, this is little of log n. This is much smaller than logarithm. But if you want to color a graph with just delta colors, then it turns out that there is no such deterministic algorithm that runs on little of log n rounds and colors acyclic graphs of maximum degree delta using delta colors. Not just graphs without delta plus 1 clicks, but graphs with no cycles. And this should remind you of the theorem of Marx I mentioned, which says that there exist acyclic graphs with maximum degree delta that cannot be colored in a Borel way using delta colors. Now, what if instead of deterministic algorithms we look for randomized ones? Well, then you can actually do something that is significantly better than log n. This is the theorem of Ghafari, Verhoeven, Kuhn, and Maus. If delta is at least 3, and then there is a randomized distributed algorithm that runs in, okay, it doesn't matter what exactly this is. The main point for me is that this is little of log n little of log n round randomized distributed algorithm that delta colors graphs of maximum degree delta without delta plus 1 clicks. And this is in parallel to the measurable Brooks theorem that I mentioned earlier, which says that instead of Borel colorings, you want measurable ones, then the Brooks theorem holds, right? And here this corresponds to going from deterministic to randomized algorithms somehow. So these are kind of uncanny parallels, and this is just a small sample of these things that you can notice that are similar in the two areas. I also hope to show with these proof sketches that they gave you that even the sort of proof techniques are at least superficially similar to each other. So is there something deeper going on? Are these just coincidences? Well, as you can guess, of course, the answer is no. There is indeed a general result that general results that you can prove that establish precise links between these two areas. At least what you can show is that efficient distributed algorithms yield colorings of infinite graphs with regularity properties. So here's the statement. This is somewhat of a special case, but this is a good enough illustration. So fix k. This is going to be our number of colors, and fix some class of finite graphs. This fancy G that is closed under adding isolated vertices. This is, you can remove this condition, but it makes the statement a bit easier. Now, suppose that there is either a deterministic or a randomized local algorithm for proper coloring n vertex graphs from this class using k colors and little of log n rounds. Now, if we're given a Borel graph G of finite maximum degree, all of whose finite induced subgraphs are in this family, then if the original algorithm was deterministic, the Borel chromatic number of G is at most k. We can conclude that the Borel chromatic number of G is at most k. And if it was randomized, we can conclude that the measurable and bare measurable chromatic numbers are at most k. Actually, you can do even something better under some additional assumptions, some continuity requirements on the graph G. In the deterministic case, you can replace this bound, instead of just talking about Borel chromatic numbers, by continuous chromatic numbers. So you can get even better. So in short, deterministic algorithms running in little of log n rounds give you Borel or even continuous colorings, and randomized algorithms give you measurable and bare measurable colorings. That's the summary of this result. So just again to illustrate, I mean, what does this tell us? Well, it explains some of these parallels I showed, but also you can use it to prove new results in, say, descriptive combinatorics by using known distributed algorithms. So here's an illustration of this. Again, we discussed this, right? There's the Brooks theorem and the measurable Brooks theorem of Conley, Marx, and Tucker-Drob. Well, since we already know the Brooks theorem is true, we can state this second theorem by saying that in the following way, that Borel graph G of finite maximum degree delta at least 3 has measurable chromatic number at most delta, even only if its ordinary chromatic number is at most delta. So of course, the left to right implication is obvious, but this measurable Brooks theorem provides the converse, that if once you can color abstractly the graph with delta colors, you can do it measurably. It turns out that you can improve this by replacing delta here by significantly smaller numbers, like delta minus some c, where c is not too big, but grows with delta. It's at most something like square root of delta. Then still the same equivalence holds. So in particular, if delta is large enough, you can write here, you know, delta minus 1, delta minus 2, delta minus 100, etc. Well, delta has to be large enough for this to work. Bigger than some constant, like 10 to the 10. Okay. Oh yeah, and the same true for bare measurable chromatic numbers. And how does one prove this? Well, once you know this connection with distributed algorithms, the proof is one line. Here it is. Balmas and Esperet, based on the work of Moller and Reed, recently constructed a randomized local algorithm that runs in little log n rounds, that given a graph of maximum degree delta and with chromatic number at most delta minus c, where c satisfies the same condition as here, produces a coloring with this many colors. So just by knowing that the coloring exists, it actually finds such a coloring. And and because of this, you can now say that, oh, look at the graph G that we have here, whose chromatic number is at most delta minus C. So every finite subgraph has chromatic number at most delta minus C. So this algorithm gives us a measurable coloring with delta minus C color. So it's immediate from the result. But yeah, by the way, the bound on C here is almost sharp. You might wonder why the square root of delta minus 5 over 2 comes up. It's because you cannot even replace it by square root of delta minus 1/2. So it's it's really close to being best possible. Not very much. Okay, so this is one illustration. You can do it, but it turns out the point is that distributed algorithm computing is a very well studied subject, and a lot of very impressive work has been done there. So there are a lot of things that are known about distributed algorithms that were maybe not known in descriptive combinatorics, but you can just translate all of those results into the descriptive setting. So I have one more application here, but I'll skip it in the interest of time. Let's scroll through it. You see, there's some theorem, some bounds on measurable chromatic numbers you can get. Okay. The point is that there are many such examples. But I would like to maybe spend the remaining few minutes talking a little bit about whether or not you can get a converse of this theorem. What happens if you try to go the other direction? So I've always been jealous of Kronecker. Everybody has theorems or conjectures named after him, and Kronecker had a Jugendtraum. So, here's my Jugendtraum. Find some kind of finitary and purely combinatorial equivalence to descriptive regularity notions. In other words, statements about, say, measurable chromatic numbers or Borel chromatic numbers, find finitary things that are equivalent to them. Like instead of saying that there is a measurable chromatic numbers at most something, say that maybe there is an algorithm that finds the coloring of finite graphs with that many colors, or something of this sort. And distributed algorithms provide something of a partial solution. So at least it's definitely a step in the right direction. We already know that this implication, that distributed algorithms yield colorings with regularity properties, you can ask whether you can go back, or when can you go back? Given the coloring with regularity properties, can you use it to construct an efficient distributed algorithm? And turns out that the answer is, at least in some cases, yes, and in some cases, no. To explain where you can go back this way, it's convenient to focus on the special subclass of graphs, namely graphs induced by group actions. This is a very natural family of graphs to consider, and they're kind of well behaved. And these are the graphs that appear in a lot of applications as well. So how does this work? We take a finitely generated group gamma with a fixed generating set S, and I'm assuming that S doesn't contain the identity to avoid some pathologies. So the Kelly graph of this group with respect to this generating set is, as usual, defined by setting the vertex set to be the group itself, and you put edges between every group element gamma, and sigma times gamma for all sigmas in S. Similarly, if you have or more generally, if a group gamma is acting on some space X, you can define the Schreier graph of this action, GXS, by making the vertex set to be X, and edges join each point X to sigma times X for every sigma in X. So the Kelly graph is like the Schreier graph of the left multiplication action of the group on itself. I'm going to focus on actions that are free, meaning that the stabilizer of every point is trivial. And in this case, every connected component of the Schreier graph is isomorphic to the Kelly graph. So really, this Schreier graph is a whole bunch of combinatorials, just a whole bunch of copies of the Kelly graph of the group. But they're somehow arranged with each other into this space, together into this space X. So in this setting, the following equivalence is true, and this is a result due to myself and independently Grebek, Jackson, Rojan, Seward, and Vidnyansky. A preprint will be appearing in the archive soon, hopefully. So this is our setting. We have a group with a finite generating set. Then what we're going to do, we're going to look at continuous colorings of Schreier graphs. So so of course if you look at an action on, say, zero-dimensional Polish space and look at the Schreier graph, the continuous chromatic number would depend on what the space and what the action are. But maybe we want to look at the maximum chromatic number that you can get. So I guess we're fixing number k, and we're saying that for every free continuous action on a zero-dimensional polar space, the Schrage graph admits a continuous proper k coloring. This actually is equivalent, as it turns out, to saying that a particular, you can explicitly describe a specific natural action like this for which the continuous chromatic number is maximum. This is the free part of the Bernoulli shift. If you don't know what this is, then don't worry. If you do know, then great. And if you don't know, this is just a specific natural example of an action of a given countable group. It's a continuous action on a zero-dimensional polar space, and this Schrage graph says that this Schrage graph has largest possible continuous chromatic number over all such Schrage graphs. And this statement in turn turns out to be equivalent to saying that there exists a little of log n round deterministic local algorithm for proper coloring n vertex subgraphs of the Kelly graph of the group with k colors. So the result that I mentioned previously implies that the third bullet point yields the first one. Once you have such an algorithm, you get continuous colorings. I said that you can get continuous colorings under some assumptions that are satisfied by these Schrage graphs. So, and of course, the first bullet point implies the second one. So the content here is that the second bullet point implies this third one. Having a continuous coloring of this graph gives you an efficient deterministic algorithm. I think this is interesting in its own right as an equivalence of these statements about continuous colorings on the one hand and these algorithmic statements on the other hand. But also these things are interesting for independently of each other and have been actually studied independently, and some known results end up being equivalent to each other because of this. So a very nice example is this work of Gao, Jackson, Cron, and Seward on continuous colorings of actions of abelian groups Z to the D, where they analyze in particular chromatic numbers of their Schrage graph, continuous chromatic numbers of their Schrage graphs. And on the other hand, there is a work of Brandt et al. I think there are 9 authors on this paper, so I couldn't list all of them on the slide, where they studied distributed algorithms for coloring grid graphs, finite grid graphs. And some of the results end up being just equivalent to this correspondence. All right, so this is the continuous setting, and just this is my last slide. What can we generalize this first? So on continuous setting, this is really in some sense a great success story, right? These continuous colorings are exactly the same as these efficient deterministic local algorithms. This exactly answers this question about getting a finitary characterization. What about, say, measurable colorings? We know that randomized distributed algorithms yield measurable colorings. So you can hope maybe to go back and say that measurable colorings yield randomized local algorithms. Unfortunately, this is not the case. You can find examples where measurable colorings exist, but no efficient randomized exist. But nevertheless, I still retain hope that there is something here even for measurable colorings. It's something we just don't have the right notions maybe isolated yet. We don't need to talk about distributed algorithms, something maybe more subtle than that to get the right combinatorial characterization. And one of the reasons why I believe that something like this can be possible is that even though there is no such formal correspondence, it is still sometimes possible to apply techniques from descriptive combinatorics to get results in distributed computing. And a nice recent example of this is there's this theorem of Grebic and Pihorko, which answered a long-standing open problem in measurable colorings. It's about edge colorings. Suppose we want to color edges of a graph rather than vertices in such a way that edges sharing a vertex are colored with different colors. Well, of course, if there's a vertex, if the graph has maximum degree delta, so there is a vertex with delta neighbors, the delta edges incident, all the delta edges incident to this vertex will have to have different colors, so you need at least delta colors. And the classical theorem of Wiesing says that delta plus 1 colors are always enough for this. So the open question was whether or not you can get such a delta plus 1 edge coloring that is measurable. And that's what Grebic and Pihorko did under some minor technical assumptions I don't want to get into. So Borel, under these assumptions, Borel graphs of finite maximum degree delta admit measurable proper delta plus 1 H coloring. There was a similar open question in distributed computing. Okay, we know that these, now we're in the finite world, we want to know that these finite graphs have colorings with H colorings with delta plus 1 colors. Can we find such a coloring using an efficient distributed algorithm? And it turns out that we can, but the notion of efficient is not quite little of log n. You know, it's polynomial in delta and log n. So ignoring the dependence on delta, the point is that it's polynomial in the logarithm of n somehow, but it's still, you know, non-trivial. And the algorithm actually is deterministic even in this case. And the point I'm trying to make is that this theorem, although it doesn't, the proof doesn't actually mention descriptive combinatorics explicitly, but it uses some of the tools, some of the main tools there are those that were developed by Grebek and Pihurko in their proof of this measurable result. So somehow it seems that once you prove a measurable theorem, it is reasonable to conjecture that maybe the same technique can be used to get a distributed algorithm, maybe with some extra work. So maybe there is some more going on. Maybe there's some more fundamental connection between these two things that we haven't figured out yet. And just to finish, since it's good form to finish on an open problem, it is entirely consistent with our current state of knowledge that there exists actually such a distributed algorithm, a randomized one, that runs in actually a little law of log n rounds. And this is true. This would imply the Grebek-Pihurko theorem and even get rid of these minor technical assumptions. But I don't know how to do this, and this I think is a very interesting question. And that's all. Thank you very much.
Thank you, Anton. Are there any questions to Anton? Yeah, I guess I'll ask you later because there is I have some questions, but I'll ask you later because there is Charles Steinhorst's talk starting soon. So if you like, first of all, let's thank Anton again for a wonderful talk. Next, if you would like to join Charles Steinhorst's talk, please log out and log in, join with a separate button. Thanks, Anton. Thanks, everyone.
Thank you.